Hello, I am Ahmad, and in this video, we are going to talk about the concept of anchorage length and how we need to find out what is the required anchorage length in a concrete element. Also, we will cover the regulation and the relevant clauses from Eurocode 2 to be applied for any concrete element. For now, in this video, we will focus on longitudinal reinforcement. So the idea of anchorage length comes from the slipping or the bond relation between the reinforcement and the concrete element. Assume we have a beam which is reinforced by reinforcement on both sides of the beam, and it's under positive bending moment. As a result, the bottom reinforcement will be in tension, and the top one will be in compression. We know that the compression is taken mainly by the concrete. So if we do not have enough length inside the concrete from the point that we have this tension, then that reinforcement will slip from the concrete. The reason is that it doesn't have enough anchorage inside the concrete. To understand it better, assume we have a concrete block in two conditions. In the first one, assume that you have a reinforcement inside the concrete with, let's say, 50 millimeter only. And in the other one, assume that we have reinforcement inside the concrete for 300 millimeter. So here we have 50 millimeter and here we have 300 millimeter. If we apply the force to this reinforcement, so we can see that the first one, which is in the left, is susceptible to fail. We can see that in case number 1, the anchorage length is quite short. As a result, if we increase the force T, then before we reach to the capacity of the rod in terms of actual stress, then it can pull out. As a result, we say that we do not have enough anchorage length in this case. But in case number 2, we can see that it has more and better resistance to be kept inside the concrete. And the main reason is that it has enough anchorage length. So for this reason, in any code for concrete structures, we need to ensure that we have enough anchorage length after the point that we have the maximum stress in the reinforcement. Otherwise, it can slip. And one of the assumptions in designing of concrete elements is that the bond between reinforcement and concrete is ensured and it is secured, that we have a very good bond that the reinforcement cannot slip from the concrete. As a result, we need to calculate what is the required anchorage length. So now, before we start to talk about Eurocode and how to calculate the anchorage length, let's have a simple calculation to understand how to determine the anchorage length. Suppose we have a reinforcement with the diameter of phi, which from the maximum stress is inside the concrete with the length of L. And it is under the tension of force T. We have two stresses in this reinforcement. One is actual stress, which is applied to the cross section of reinforcement, and the other one is the shear stress or average shear stress in the total length of reinforcement. If we sketch the reinforcement, we have also ribs that in this calculation we can assume that it's smooth. Force T is applied and the diameter of reinforcement is phi. And the embedded length is L. So now the actual stress can be calculated according to force divided by area. So force here is T and the area is pi p squared divided by 4. And also in the length of L, we have also this shear stress in the peripheral area of this rod. So tau is again the force divided by area. The force is T, but the area is the peripheral area of this rod. So we need to calculate perimeter of the reinforcement and multiply it by the length. So pi p is the peripheral length times L. Let's go with a very simple example to calculate these two. If allowable axial stress in a rod is 300 megapascal and the allowable shear stress is 3 megapascal. Determine the maximum tension that the bar or the rod can withstand. Diameter of the bar for the rod is 20 millimeter and the embedded length is, let's say, 600 millimeter. So we know that sigma allowable is 300 megapascal and this is T divided by pi 20 millimeter square divided by 4. As a result, T based on the failure in the actual stress is 300 pi 20 squared divided by 4, which is 94 kilonewton approximately. And according to tau, which is only 3 megapascal, T divided by pi, P is 20 millimeter and L is 600 millimeter. based on the shear resistance of the rod, it is 113 kilonewton. And if we want to say what is the maximum capacity of this rod, P max will be minimum of P because of axial resistance and T because of shear resistance. So it will be 94 kilonewton. Now, coming back to the topic, from these two equations, we can determine what is the maximum capacity of one element. From the first one, P due to axial stress will be sigma times pi P square divided by 4. And from the second equation, P shear will be tau times pi V times L. If we have a certain value of sigma in the rod, then we prefer that the failure is not happening to shear resistance because we assume that the bond is 100% secured. So we can write down this way. To secure bond connection between concrete and reinforcement is valid, E in shear calculation should be always equal or greater than T from axial force. If I substitute these two equations, then tau times I times V times L should be greater or equal to sigma times pi phi squared divided by 4. And if I simplify this pi with pi, 1 phi with this one, then L needs to be greater than sigma times phi divided by 4 tau. This is the basic required or the basic anchorage length. So if we write down sigma as the stress in reinforcement, and if we write tau as FBD or shear stress resistance between concrete and reinforcement, then the equation will be L should be greater than Fs times phi divided by 4 FBD, which is the given equation in Eurocode. And also in many other codes, the concept is the same. Now let's review what Eurocode says. It starts from chapter 8, Anchorage of longitudinal reinforcement, clause 8.4. Reinforcing bars, wires, or welded mesh fabrics shall be so anchored that the bond forces are safely transmitted to the concrete, avoiding longitudinal cracking or spalling. Transfer reinforcement shall be provided if necessary. For example, sometimes you do not have enough space to have long anchorage length. As a result, we can confine them with the transverse reinforcement. Methods of anchorage are shown in figure 8.1. A, this is the basic tension anchorage length. LB for any shape measured along the center line. One important note is that it's always from the center line. If you have a 90-degree bend, then equivalent anchorage length for a standard bend is calculated as we can see here. From the point that you have the maximum length, you need to have enough anchorage length. This is the equivalent anchorage length. And also if you bend it, then you need to have at least greater than 5 times phi for the reinforcement. If you have more than 90 degree or more than 150 degree, then equivalent anchorage length is shown in the point C, and you need to have again 5 phi. And also in point D, when we have the U shape reinforcement anchored from the point that you have the maximum tension or stress. And part E is for equivalent anchorage length for welded transverse bars. As we noticed, I changed the notation of how to FBD. This is the ultimate bond stress, which is given in clause 842 in Eurocode 1992.11. The ultimate bond strength shall be sufficient to prevent bond failure. The design value is calculated according to the given equation 8.2. FCTD is the design value of concrete tensile strength, and we need to calculate according to 3162 plus 3162, and there is also FCTK 0.05, and this is important that FCTK 0.5 should be limited here to the value of C6075, unless it can be verified that the average bond strength increases above this limit. Apart from that we can take from the other clause in Eurocode, we have eta 1 and eta 2 that we need to calculate. Usually we use E up to 32 millimeter. As a result, eta 2 is here, so it's 1. If it is greater, then we need to apply the adjacent equation. And eta 1 is the coefficient related to the quality of the bond. If we look at the concrete elements, if they are very deep, then in reality, the bottom of the concrete will be more dense compared to the top level or upper levels. As a result, usually we need to differentiate between two bars, which one is in the dense layer or it is in the loose layer. In Eurocode, we have this good and poor condition. So if you have a good condition, then eta 1 is 1. If you have a poor condition, then eta 1 is 0.7. As a result, we decrease the bond stress that can be taken by the reinforcement. So FCTD is given in clause 316. And have a look on that. 316, and here is FCTD calculation. Gamma C is given in 2424, which for concrete is 1.5. You can check the table. And alpha CT is the coefficient taking the long-term effect, and you can find it in National Annex, or the recommended value is 1. FCTK is the value that we need to find out from the table 3.1 in Eurocode. It's the characteristic tension resistance or tension strength of concrete. So in table 3.1, from the strength class of concrete, we can find FCTK 0.05. Or if you are writing a code for R&D, then you can use the given equation in the explanation or analytical relation. So from here, we can take FCTK 0.05 and then we can substitute it in this equation. Alpha CT is 1, gamma C is 1.5, and then we can calculate FCT. Then we can come and check what is the condition for eta 1. If it is good, then eta 1 is 1. If it is poor, then it is 0.7. Eta 2, according to the diameter of the bar, can be determined, and then we will have FBD, which is representing the ultimate shear resistance between the reinforcement and concrete. The only thing that is missing here is the good and poor condition of reinforcement. The condition or description of bond conditions is given in figure 8.2 in Eurocode 1992-11, and A represents the direction of concreting. So then in the correction version, they use the upside down arrow instead of this sign. The reason is that the direction of concreting is from bottom to the top, but we know what it means, so it's perhaps it would be better to write the direction of pouring concrete. But in any case, we can understand the figure. So if we have a bent bar, then it's always good condition. As we can see, A and B, good bond conditions for all bars. So if we start to bend, then it's always good condition. If the thickness of the element which is concreting is less than 250 millimeter, so perhaps the variation between the bottom and the top might be neglectable. As a result, we assume that it's always a good condition. So for these two cases, we can assume eta 1 is 1. In C and D, unhatched zone is good bond condition, and the hatched part is poor bond condition. Here we can see if the element height is greater than 250 millimeter but less than 600, because at D we have greater than 600. So part C is applied to edge between 250 millimeter up to 600 millimeter. The first 250 millimeter is good condition. As a result, for the bottom reinforcement, we can assume it's in a good condition. And for the reinforcement above this level, or let's say up to 350 millimeter, after this maximum 350 millimeter, that reinforcement located on that direction is always poor condition. And if the height of the element is greater than 600 millimeter, then only 300 millimeter from the top is assumed for being in poor condition. That's how we can determine if the reinforcement is in a good condition or is in a bad condition. After we determined FBD, then it's time to calculate the basic anchorage length. So here we can see that this is exactly what we calculated. The equation given in 843 number 2 is LB required, which is phi divided by 4 times sigma SD or Fs divided by FBD. Number 1, the calculation of the required anchorage length shall take into consideration the type of steel and bond properties of the bars. The basic required anchorage length LB required for anchoring the force AS times sigma SD in a straight bar, assuming constant bond stress equal to FBD follows from this equation. This is important to understand what sigma SD is. Sigma SD is the design stress of the bar at the position from where the anchorage is measured. So this is the design stress. Usually it is taken F by D as it is the maximum. But I have faced a few projects that we had to change or use a smaller anchorage length. As a result, it is important if in a project you are facing similar difficulties, then we can use this clause to decrease the anchorage length. Values for FBD are given in 842. We already determined that. And for bent bars, the basic anchorage length and the design length should be measured along the center line of the bar. We had this graph as well earlier. So this is the basic required anchorage length, and it should be multiplied by several factors to calculate what is the designed anchorage length. For that, we need to follow the next clause in Eurocode, which is coming in clause 844. The design anchorage length LBD is a multiplication of alpha 1, 2, 3, 4, 5 LB required. It should be greater than the minimum value of this length. Alpha 1, 2, 3, 4, 5 are taken from table 8.2. Alpha 1 is for the effect of the form of the bars, assuming adequate cover. Alpha 2 is the effect of concrete minimum cover. Alpha 3 is for the effect of confinement by transverse reinforcement. Alpha 4 and 5 are also about the confinement of the reinforcement. Usually alpha 3, 4, 5 can be taken as 1 if you do not have any welded transverse reinforcement like stirrups. And always we need to check alpha 2, 3, 5 are greater than 0.7. LB minimum is the minimum anchorage length, and for tension it should be greater than the maximum of these three values. And if it is in compression, then the L minimum is calculated according to equation 8.7. For calculation of alpha 1, 2, 3, 4, 5, we need to check the table, but before than that, the same clause, part 2, as a simplified alternative to 8441, the tension anchorage of certain shapes shown in figure 8.1 can be calculated for B to D, alpha 1 times LB required, and for 8.1e, we can just calculate alpha 4, which is related to transverse reinforcement, which is welded to the longitudinal reinforcement. Usually we can assume all of these factors are 1, and then we can just calculate the value according to LBD, which is equal to LB required. But from time to time you might face something difficult and you want to decrease the anchorage length. If you are designing in compression, typically alpha 1, 2, 3 are all 1 and alpha 5 is not applied. And if you have a welded transversal reinforcement, then you can use 0.7. But for tension, we have different criteria for calculation of alpha 1, 2, and 3. In this video, we just cover alpha 1 and alpha 2. You can read about alpha 3, 4, 5 by yourself. So for calculation of alpha 1 and 2, we need to understand these 3A, B, and C. In A, we are talking about straight bars. In B, bent or hooked bars, which are bent upward. And in C, they are looped. The difference, if we want to sketch, if this is the corner of the element that we are talking about for calculation, and assume that this is reinforcement. So these are longitudinal reinforcement inside the element. C is the distance between the edge of concrete to the edge of reinforcement. And C1 is for the end member. A is the clear distance between two reinforcement. You can assume that the reinforcement diameter is 1.1 times the diameter of the reinforcement considering the ribs. And in A, we can calculate CD as minimum of these three values, A divided by 2, C1 and C. Similarly for the bars which are bent upward. So A is the distance, clear distance between two longitudinal reinforcement which are bent upward or as a hook, and C1 is the end distance in the horizontal direction. So CD can be calculated according to the given equation. And for the looped bars, if we look at from the top, we will see that they are overlapping each other in the loop. After calculation CD, then we can come to the table for straight bars. Alpha 1 is always 1. If you have other than this, for example, a hooked bar, then alpha 1 can be calculated according to be 0.7 if CD is greater than 3 times B. And for alpha 2, we can calculate according to the given equation for straight bars. Alpha 2 is calculated from the equation and it should be greater than 0.7 and also less than 1. It should be in this range. If it is not straight, then we can use the other equation, but still we need to keep the limits. And if you are interested, there is a footnote at the end of this table of coefficients for calculation of alpha 1, 2, 3, 4, 5. This is related to alpha 3, which you can calculate lambda. And now you can calculate the anchorage length of the reinforcement. Now it is good if we have a simple example how to calculate the anchorage length. Assume the beam shown in the figure is made of concrete C3037 and is designed with 4025. Determine the required minimum reinforcement length So we are talking about C3037 and the diameter is 4025. And let's sketch the beam. You have a 5 meters beam and the dimension of the beam is 300 by 450, for example. (4025). We need to follow the minimum reinforcement in both sides, and it will be covered in the other video. So now we are talking about the reinforcement which is coming here. And as far as in the middle of the beam, if the beam is under distributed load, This is the place that we would expect we have maximum bending moment. So now, first of all, we need to calculate what is the base anchorage length. So L be required will be phi divided by 4 times sigma SD divided by FBD. Sigma SD is the stress in the reinforcement, and practically it is used to be FYD. I will record another video regarding the calculation of this sigma SD, but for now we can follow FYD, and usually we use AH or B500 as the reinforcement. This means that Fy of the reinforcement is 500 megapascal. And according to Eurocode, we need to calculate what is FYD, which is Fy divided by gamma S. Gamma S is given in Eurocode chapter 3, I suppose. And for steel, it is 1.15. So 500 megapascal divided by 1.15 is 435 megapascal. Diameter of the bar is 20 millimeter. And then we need to check what is FBD. So FBD is determined according to the equation 8.2, which is 2.25 eta 1 eta 2 times FCTD. So the reinforcement is going to be in the bottom because we have maximum positive bending moment. As a result, the bottom of the beam will be under tension. And as far as it is close to the bottom and it is between 250 and 600, we assume that it has a good bond. Good bond condition. As a result, eta 1 will be 1. B is 20 millimeter and it's less than 32 millimeter. As a result, eta 2 is also 1. And then FCTD, according to chapter 3, is alpha CT multiplied by FCTK 0.05 divided by gamma C. Gamma C is 1.5, alpha CT is 1, and we need to check what is FCTK 0.05 for C3037 by using table 3.1 C FCK 30, FCTK is 2 megapascal. As a result, FCTD will be 2 divided by 1.5 and it will be 1.33 megapascal. Now we have FCTD and we can calculate what is FBD, which is 2.25 eta 1 eta 2 FCTD. And substituting the values would result in 2 or 2.99. It's 3 megapascal. So if we have FBD, then we can calculate what is the required length, which is phi divided by 4 times FYD divided by FBD. So phi is 20 millimeter divided by 4 times 435 megapascal divided by FBD, which is 3 megapascal. So it will be 5 times 435 divided by 3, and then it's 725 millimeter for a good bond condition. So this is the required length. And as far as its straight bar, so we can take alpha 1, for alpha 2, we can calculate to see if it is applied to use a smaller than 1. Alpha 3, 4, and 5 also we can assume they are 1. Notice that as far as you have a stirrup in the beam, you can decrease the value of alpha 3. Also, there is another way to decrease the length of the anchorage length, considering what is the sigma st that I will cover it in at some point in the other video. So now LBD will be alpha 1, alpha 2, alpha 3, alpha 4, alpha 5 times LB required, which should be greater than LB minimum, which is maximum of 30% LB required, 10 times phi and 100 millimeter. So this value will be 30% of 725 to 117.5 millimeter. 10 times phi is 200 millimeter and 100 millimeters. So, and this value will be 725 millimeter, and it is greater than 217.5. So LBD is 725. The important point is where we need to consider this length. If this is your beam, it is not in a scale. The maximum stress would happen always in the center if the beam is under distributed load or vertical load symmetrically. So this is the maximum bending moment. As a result, if we cut the section from this point, our reinforcement will be under maximum tension from one side. So it means that this is under E max. And from this point, we need to govern the required or the anchorage length. So this should be LBD. Also, if you cut it from the other side, again, you have T max, but this time from the cut towards the right of the beam, then we need to provide LBD. So the minimum length of the reinforcement should be 2 times LBD in this case. So 2 times 725 is 1450 millimeter. Notice that we cannot cut all of the reinforcement. We need to keep some of them to ensure that we have the minimum reinforcement. Back to several years ago, it was important to cut as many as possible if the reinforcement was not needed. But nowadays, at least I can see that there's no cut. One reason is that, for example, here in Finland, the cost of labor work is much higher than the cost of the material. As a result, it is preferred to buy the material. However, if you are in a company which is optimizing the design and you are taking care of the sustainability, then this is the way how we can save the material as well. Especially those companies who are that are designing the precast elements, they might have a better condition for using material and saving the material. So this would be very useful, even though the beams are usually designed or precast are based on pre-stress element. Well, that was the end of this video, and we went through the anchorage length calculation according to Eurocode 2. We check the clauses that you need to check when you want to determine what is the anchorage length and the concept of how it is designed. And also we went through one simple example. In the next two examples, I will go through the calculation of anchorage length for one slab and then the other one for a foundation, which would be very interesting and very practical. Thank you for watching. See you next time. Bye.